So let me just do this quick review. This is about head loss in a long straight pipe, and it's long and straight, and that means that the losses are mainly due to shear on the wall of the pipe, and that's causing that shear is trying to slow the fluid down or requiring a higher force to be applied to push the fluid through. So for laminar flow, meaning for low velocities, low Reynolds numbers, we have this beautiful relationship where the friction factor is 64 over the Reynolds number, and that leads to the Hagen-Poiseuille equations. And we get this really nice result where the head loss or the change in water elevation required to push water through a tube is directly proportional to the flow rate or the velocity that the water or the fluid has going through that tube. So that direct proportion is something that we're going to end up using to design a flow controller for dosing our chemicals. In turbulent flow, you have a higher Reynolds number above 2100, and now F is no longer a beautiful equation. There it is. It's a mess. It's related to how rough the surface of the channel or pipe is. That's that epsilon, and related to the diameter as well. And of course, the Reynolds number is in there. So that's a Swamy-Jain equation. Basically, it is a dimensionally correct fit to the experimental results where people actually measured the head loss in various pipes. And unfortunately, there's no simple equation that comes out of this. But hey, that's what computers are for. Computers can solve this equation for us and make this easy to use. So there's the Darcy-Weisbach equation. And by the way, the Darcy-Weisbach equation written in that form, HF is equal to that friction factor times L over D times V squared over 2G, is always true, whether it's laminar flow or turbulent flow. Just that for laminar flow, we can plug in F is equal to 64 over the Reynolds number, and then we get the Hagen-Poiseuille equation. But for turbulent flow, we just have a mess. And so we're going to have to use computer programming to help solve this. Here's a Moody diagram, and we're showing this because this is how engineers used to, and I want to really emphasize, used to solve pipe flow problems. I think you should know what this looks like to have a sense of how this friction factor equation, the Swamy-Jain equation, what that shows, and how head loss increases, or the friction factor increases as roughness of the pipe or channel increases. But this Moody diagram is a pain to use to actually solve a fluids problem. So we're not going to do that. And I would strongly urge you to never do that in your engineering practice, because it means that your design isn't like linked together in a cohesive way. There's a place where you have to actually take a break, move away from your design work and go look at a Moody diagram and then copy a number down for the Moody diagram and continue on with your calculations. That's a terrible approach, because if you forget to do that at some point, you're going to have the wrong design. So Moody diagram is a terrible way to design anything, but there it is, to think about how people did it 50 years ago. So now I want to have you think about all these ideas and think about, okay, how could you figure out what's going to happen when you have a pipe connecting two tanks and it's carrying water from one tank to another. So we've got these two tanks. I'll show you a picture of this in a second. The current flow rate is Q. I don't know what it is. I didn't really care. The pipe diameter is 1 inch. The downstream tank water surface is 1 meter lower than the upstream tank water surface. So that's the head loss. That's the difference in energy between the one tank and the downstream tank. And you can assume these following things. And this is code for figuring out what's important in this problem. And if you were actually doing this problem as an engineer, you would want to go back at the end and verify that all of these assumptions were right. So you can assume that the flow is turbulent, and indeed there's a very high Reynolds number. You can assume that the pipe walls are rough, And you can assume that the pipe to length over diameter ratio is large enough that major losses dominate. So let's go back to the first one. The flow is turbulent. That means we're on this graph and the flow is turbulent, and it's very turbulent, which means we're at a very high Reynolds number. And the pipe is rough, which means we're up here somewhere. And what you see is that all of these lines are basically flat, meaning F is constant. So if you have high Reynolds number and rough pipes, the friction factor is constant. So that's what you can learn from these first two statements. So now we know that the friction factor is constant. And now point 3, the pipe length to diameter is large enough that major losses dominate. So here are the two equations. The first equation is minor losses, meaning changes in geometry are causing losses of energy, causing turbulence that ends up dissipating energy as heat. So that's the minor loss equation. And the second one is the major loss equation. And if you compare those two, you see that the difference between those two equations is that one has KE and the other one has FL over D. What does that mean? It means that if major losses are dominating in a system, it means that FL over D is greater than K. If major losses are more important than minor losses, then F times L over D is more important or is larger than the minor loss K. And I'm telling you in this problem setup that major losses dominate. So that means that all we've got is this second equation, head loss is equal to FL over D times V squared over 2G. And from the first two assumptions, you know that F is constant because it's very turbulent and it's a rough pipe. So now the question. Estimate approximately, no calculations, okay? No writing down stuff on with paper and pencil, just that you can do this whole thing in your head, okay? Estimate approximately how much further must I lower this downstream tank to double the flow rate. So right now I've set this up. So these two tanks, there they are, and they've got a water surface in them. And that water surface is 1 meter lower in the second tank than in the first tank. And that's what's driving the water through that pipe. And I want to know how much more must I lower the downstream tank, or how much difference in water elevation do I need to have in order to double the flow rate? And you can assume that when I move these tanks around that the pipe remains the same length. So, and remember this problem very carefully. It's estimate approximately how much further. So right now there's 1 meter here. How much further must I lower this in order to double the flow rate? I'm going to drop that second tank a certain number of meters. How many meters do I need to? We're seeing 3 different answers. The most popular one is 1 meter, and then there's several with 3 meters, and then there's one or more with 4 meters. So the cool thing is, this is engineering and physics, and so it means that there actually is one right answer. And so the question is, what is going on? Because clearly, you know, we don't all agree on what this answer is. So let's go back and look at what's happening. Okay, so we want to lower this second tank a certain number of meters so that this flow doubles. Okay, so the thing I want to look at is which equation is going to be so helpful here. And it's this second equation here, that the head loss, oh, sorry, thank you for pointing out that I wasn't sharing my screen. I just get all happy and I'm looking at my screen and I can see it just fine. Okay, so we're looking at how far do I have to lower this second tank to double this flow rate through this pipe? Okay, that's the question. And now we go back to our friendly equation that describes the physics for this. And that is this Darcy-Weisbach equation that says that the head loss, that this is how much energy is going to be required to push the water through that pipe, is equal to FL over D times V squared over 2G. And we previously argued that F was a constant, that F isn't changing with flow rate because we are on the Moody diagram in this place here where F is relatively constant over a broad range of Reynolds numbers. So back to this equation, F is a constant, the length is a constant, the diameter is a constant. So this first part here is a constant, and we are going to double the flow rate, which is the same as saying we're going to double the velocity. So V, we don't know what it was before, but before V squared over 2G times FL over D got us a 1. Now we're going to double V. And that means when we double it, instead of getting a 1, we're going to, because we're squaring it, we're going to get a 4. Everybody see that? When I double V, I don't get twice as much head loss. I get 4 times as much head loss. So the head loss, the total head loss, instead of being 1 meter, is going to be 4 meters. And then back to this question, I've got to drop it an additional 3 meters to get a total of 4 meters of head loss. Okay, so I think like 80 or 90% of you did not agree with that analysis. So I would love to take a question if you have some about that. Look, you know, part of what's happened is I have learned over years of teaching which questions students just completely miss. So I kind of expected that a large number of you would miss this question because head loss is complicated and it's just easy to not understand this. So my goal of asking you to fight through that question was to recognize that, oh, this is a little more confusing than what I thought. And now I'm hoping that it makes sense. Because this idea that head loss increases really fast when you increase the flow rate when it's turbulent is like an important insight. You double the flow rate and you quadruple the head loss. Anybody want to jump in with a question? Or a complaint? Why did Monroe humiliate all these students? That was not my goal. Because this is a safe environment. This isn't, you know, your engineering consulting firm where you really ought to get the answer right. Okay, everyone's quiet. So I'm going to continue. And what the last thing I wanted to do today is I wanted to do a demo of making this this pipe system of these tanks and this pipe in Onshape. So I'm going to quit this and I'm going to pop into Onshape, and you should still be seeing this screen, right? You're now seeing Onshape. So I wanted to just do this fun demo of let's make that design that I just showed you of 2 tanks and a pipe. So in order to do that, I'm going to let's begin by creating a configuration variable that will be the head loss. Hang on, let's do this right. Let's just I'm just going to call it HL. Okay, and it is a length, and its default is 1 meter, and it's sure, but let's not go to, let's just say the maximum is 10 meters. Okay, and that will pop. There's my head loss right here. Okay, so I got my variable, and I'm going to pop a tank in here, and you should be adding these features to your list of custom features as well. So here's the civil tank. I'm not going to worry about implementation partner, and I don't know, let's make this tank be a meter by a meter and by a meter, and there's only one section, and we're going to pop it right at the origin. So I'm clicking here on the location, and I'm going to pop it right here on the origin, and there's my tank. And okay, I wanted to have an open tank, so I don't want to top on it. So I'm just going to click on this to get rid of the top, and now I've got my nice little open tank. Okay, so that's my first tank, and now I can add my second tank. And to add my second tank, I'm gonna hide this first tank so it's not getting in my way, and I'm going to add a second tank. And this one, I'm going to also make it be same size, 1 meter by 1 meter, and one tank and no top. And I'm going to put it on the origin, except I'm going to then go in and I'm going to edit its location. So I popped it in at the origin, but now I'm going to go edit this mate where it's being brought in. So I'm going to click on this mate connector, and this gives me an option for moving it. And I'm going to move it, let's move it like 10 meters over to in the X direction, which is going to move it over to the right. So it just disappeared. There it is. Okay, see there, it moved way over there. Here's the origin, and there's the tank. And I also want to shift it down. I'm going to drop it by head loss. I'm going to move it down by the head loss, which is the parameter that I created. And so that just lowered it. Okay, so now let me show all my parts again so you can see what happened. I got my two tanks. I inserted them both at the origin, but then the second one I moved over 10 meters and down 1 meter. And so now I have my two tanks. Just for fun, I'd like to put a water surface in here. So let's do that. I'm going to make a sketch, and I'm going to put that sketch on the front plane. So there's the front plane. And in order to draw a water surface, all I need to draw is a line at the elevation of the water surface. So let's do that. And I don't know, we're going to put it halfway up the tank. So there it is. And I'm going to do another one on the other tank. There it is. And I've got my two sketches, or I've got my two lines drawn on these tanks. Sorry, you can't hardly see them. So let me just hide the tank so you can see what's there. So I've drawn those two lines, and those lines are black. You see that? Those lines are black because they snapped to the walls of the tank. And so they're precisely set to be halfway up the tank and to intersect with the walls of the tank. So that's what's defined them nicely. The next thing I want to do is I want to create a surface off of those lines. So there the two lines are. I'm going to create a surface using extrude. And instead of creating a solid, I'm going to create a surface. The sketches that I'm going to extrude, I think I can just select sketch 1 here. So all of the edges in sketch 1 are selected, and I'm going to extrude them. I'm just going to use this as I'm going to just enter the number. My tank is 1 meter deep, or 1 meter long, and so I'm going to do it 1 meter. And now I have my two surfaces. And so the next step is, oh goodness, I could I could make them look pretty. I could edit the appearance for surface 1, and I could make this be blue, but I could make it be only 20%. So it's 80% transparent. And there's a transparent surface. I've done that for one. I'm not going to bother doing it for the second one, but you saw what I did to make it transparent. Okay, so now let me bring back all of this and let me, looks like my water surfaces are kind of missing the tanks. So apparently I extruded in the wrong direction. So let's go back to the extrude and let's just switch this direction. And now my water surfaces are in my tank, and you can see that nicely there. So now I have my water surfaces in my tank, and just give me 1 second. So now I have the water surfaces in my tank, and the next step is I want to draw a pipeline between these two tanks. I want to draw a pipe. And in order to do that, I need to draw a line where I want the pipeline to go, where I want the pipe to go. So I'm going to do another sketch, and this sketch, I'm going to, I have to think about how to do this. I'm going to try putting it on the front plane, but can I edit this? No, I can't edit that because I want to move it off the front plane. So that didn't work. So let me instead put it on let me hide everything again. I want to put it in the middle of the tank. So I'm going to put it on the origin, and I'm going to edit that origin. I'm going to see this mate connector here. It's currently in the XY plane, and I would like it to be in the XZ plane. So the way I'm going to realign it is I'm going to say, hey, I want that mate connector to actually line up with the front plane. And when I do that, the mate connector rotated, so it's now in the front plane. See that? So let me undo that. Mate connector was in the top plane. I said, no, I want you to realign, and I want you to be in the front plane. And so now it's in the front plane. And the other thing I want to do is I want to move it now in the Z direction. I want to move it towards the middle of the tank, which is 0.5 meter back. So if I move this 0.5 meters, and it moved back. So the mate connector moved away from the origin back into the tank 0.5 meter, and I've got that defined now. And now let me bring back the tank so you can see where this is at. So I've got this, my sketch, see that? It's now in the middle of the tank. And now what I want to do is I want to draw a line from one tank to the other tank, and let's constrain this somehow. So let's constrain this so that, hang on, why can't I move this? It's that. So right now I can't move this end of the pipe up because it picked a constraint to be level with the origin. So I want to get rid of that. So I'm going to delete that constraint. Now I can move this pipe up. And what I'm going to do is I'm going to just somewhat randomly, but I'm going to make this end of the pipe be 20 centimeters off the bottom of the tank. So I'm going to select the bottom of the tank. I've selected the dimensioning tool. I've selected the bottom of the tank. I've selected the end of the pipe, and I'm going to make that be 0.2 meters. Well, okay, that's one. And let me just slide this back in here again. So I've constrained it to be 0.2 meters off the bottom. I'm also want to constrain it to be 0.2 meters from this edge, just so that it's sticking into the tank a little bit. There's many ways you could do this, but just for demonstration here. So now I've got that end constrained, and we're going to do the same thing down at this end. So I'm going to first bring this pipe into this tank, and I'm going to say that I want the end of the pipe to be 20 centimeters from the floor. So that's 0.2. And I also want to say that the end of the pipe is 20 centimeters in from the end of the tank. So it's reaching in 20 centimeters into the tank. And now everything is black. So I've constrained that pipe or that sketch. So I'm happy with the sketch. That's where I want my pipe to go. And now the next thing I do is I grab the pipeline tool, and the pipeline feature, I need to select an implementation partner, which for now we can let just be auto. And I think I said that this pipe was actually 1 inch in diameter, and the pipe that the edges that are going to define the pipe is this sketch. So I just click on any of the lines in that sketch, and there's only one, so there it is. And that draws a pipe, okay? But it puts caps on the ends of the pipe, and I don't actually want caps on the ends of the pipe. So there's an option here for elements to avoid. So I want to avoid this vertex at the end of that line. So if I click on that vertex, it says, oh, don't put a cap on that vertex. And so remove that cap. We'll do the same thing down at this end. I'll remove this cap, and that should be good. And now if we, let's see, I can clean this up. I can hide, by hiding the pipeline here, I'm actually hiding like mate connectors and sketches and things. And so just make it look pretty. And I could, I guess as a final step, I could show you that it's all there. So I'm going to do a section view and select that as a section view, section plane, and I'm going to back it in. And so there we can look into the tank, and there's a pipe sticking into the tank. And what else happened? If I go over here to custom tables, to bill of materials, it says there's some walls on the tank, there's various pieces of concrete, and there is a Schedule 40 PVC pipe. And it gives me that this whole thing costs $647. I know that was a whirlwind, but I wanted to show you kind of the power of what you can do with Onshape with some of these tools that we've created.